The Lockheed SR-71 Blackbird remains one of history's most profound engineering marvels.
It's an aircraft that operated at the precipice of space.
And at speeds that challenged the very materials from which it was built.
This long-range strategic reconnaissance aircraft was capable of sustained flight at 26 kilometers above the Earth's surface.
An altitude so extreme that its pilots could clearly perceive the planet's curvature against the inky blackness of space.
It flew at such blistering velocities.
In excess of Mach 3.2. That the primary design challenge was not propulsion alone, but the mitigation of immense heat generated by aerodynamic friction.
The aircraft's operational record is a testament to its revolutionary design.
Despite numerous attempts by adversaries in theaters like Vietnam, North Korea, and Iraq, not a single SR-71 was ever lost to enemy fire.
Its standard evasive maneuver upon detecting a surface-to-air missile launch was simple, audacious acceleration.
While the missiles possessed a higher theoretical top speed,
they lacked the energy and maneuverability to intercept the Blackbird at such extreme altitudes.
This operational invincibility, however, was merely the consequence of a design miracle.
The entire aircraft was conceived around its propulsion system, a hybrid engine.
That had to conquer a myriad of seemingly impossible problems, from cooling and fuel efficiency
to the management of supersonic shockwaves.
The central paradox of the SR-71 lies within its engines.
The aircraft was powered by two Pratt & Whitney J58 engines, which were fundamentally turbojets.
Yet, analysis revealed that at its cruise speed of Mach 3.2,
These off-the-shelf turbojets could only provide a mere 17.6% of the total thrust required for flight.
To achieve sustained speeds of this magnitude, a ramjet is necessary.
A ramjet is an engine of elegant simplicity, deriving its name from its operational mechanism.
It rams through the air, using its forward motion to funnel and compress high-pressure air into its inlet.
This compressed air, which must be slowed from supersonic to subsonic speed before combustion,
effectively replaces the mechanical compressor stage of a conventional jet engine. Once the slowed air enters the combustion chamber, it is mixed with fuel and ignited.
And violently expands, accelerating out the exit nozzle to produce immense thrust.
While capable of operating at speeds far greater than any turbine engine, a ramjet has no moving parts.
And suffers a critical flaw. It cannot generate static thrust.
it requires significant forward momentum to initiate the compression cycle. The engineering solution for the SR-71 was thus not a choice between one engine or the other,
but the creation of a complex, hybrid system.
The J-58 was a turbo-ramjet, capable of transitioning, mid-flight, from a conventional turbojet to a ramjet.
with the turbojet engine nestled deep inside the nacelle, becoming one component in a much larger system.
The genius of the SR-71's propulsion system was its sophisticated airflow management, centered on the prominent inlet spike.
This spike was far from static. It was a critical, dynamic component, capable of moving longitudinally. Its function was to control the volume of air entering the engine by adjusting the inlet and throat area. More importantly, it managed the position of the normal shockwave.
The point at which the supersonic airflow abruptly slows to subsonic velocity.
For maximum efficiency and to minimize energy loss from drag.
This shock wave had to be precisely maintained between the inlet throat and the compressor face.
The spike's movement was automated. It remained in its forward position until Mach 1.6.
After which it began to retract 41 millimeters for every 0.1 increase in Mach number.
Meticulously keeping the shockwave in its optimal position. This system also managed the boundary layer, a layer of slow-moving, inefficient air that clings to surfaces.
The inlet spike featured perforations and ducts that bled this boundary layer off, preventing it from entering the engine.
This process freed a greater area of the inlet for high-energy, fast-moving air,
dramatically improving efficiency and ensuring the engines were fed only the most potent airflow.
Beyond the spike, a complex ecosystem of ducts and doors managed the air's pathway. A large bypass area routed air from the main inlet around the J-58 engine itself.
This bypassed air served a dual purpose. It first acted as crucial coolant for the J-58, improving its efficiency,
and then rejoined the main airflow just after the afterburner, adding mass and oxygen to increase total thrust.
This bypass was fed by several sources. A shock trap that also helped manage the boundary layer.
Suck-in doors that opened only at low speeds to provide additional cooling air. And aft bypass doors controlled by the pilot. Forward bypass doors, venting to the atmosphere, were controlled by pressure sensors to maintain optimal inlet pressure.
Mismanagement of this intricate system, particularly the shockwave's position, could lead to a catastrophic event known as an unstart.
Causing a sudden, massive loss of power in that engine and throwing the aircraft into a violent yaw.
The recovery procedure involved fully opening the forward bypass doors and moving the spike forward.
To reduce back pressure, allowing the shockwave to be recaptured.
This entire bypass system was the key to the ramjet transition.
6 dedicated bypass ducts routed air from the compressor stage directly into the afterburner.
This action transformed the afterburner from a simple thrust booster into the primary engine,
effectively turning the entire nacelle into a high-efficiency ramjet.
Given that ramjets can theoretically operate up to Mach 5, a critical question arises. Why did the SR-71 stop at Mach 3.2?
The limiting factor was not the engine's thrust, nor its fuel capacity, but the overwhelming destructive force of heat.
At Mach 3.2, the aircraft's nose reached 300 degrees Celsius. While the engine nacelles glowed at temperatures ranging from 306 degrees Celsius at the front to 649 degrees Celsius at the back.
The entire design was dictated by this thermal barrier.
The fuel, a specially formulated compound called JP7, was selected for its extremely high flash point and low volatility.
This stability was necessary, not only because the fuel tanks leaked on the runway,
but because JP7 doubled as the aircraft's primary coolant and hydraulic fluid. It was pumped throughout the airframe to cool critical electronics, hydraulic systems, and engine oil,
before being sent to the engines for combustion.
The fuel was so stable that the plane had to carry triethylbutane,
a chemical that spontaneously ignites in oxygen, just to start the combustion cycle and light the afterburners.
The airframe itself used a total wet wing system.
Meaning, the fuel was contained by the aircraft's skin, rather than by heavy internal bladders.
This saved weight, but as the skin expanded and contracted with heat, the sealant would degrade, causing the infamous leaks.
This plane was, in essence, a flying fuel tank.
At 59% of its total wet weight, it was mostly fuel, a necessity to feed its voracious engines.
Even the aircraft's iconic black paint was a thermal management tool.
Adhering to Kirchhoff's rule of radiation, which states that a good heat absorber is an equally effective heat emitter.
The black paint allowed the SR-71 to radiate the intense heat of aerodynamic friction away from its critical structure.
To survive the extreme thermal environment, conventional materials like aluminum,
The plexus used on the Concorde, which was limited to Mach 2, were insufficient. The SR-71 was composed of 93% titanium alloys.
Titanium possesses a fantastic strength-to-weight ratio.
But its true benefits are its ability to resist heat and its low thermal expansion. Titanium alloys can retain their structural integrity at temperatures up to 600 degrees Celsius,
where aluminum would have long since failed. However, titanium is incredibly expensive to refine and notoriously difficult to machine,
as it reacts with air and becomes brittle during forging or welding.
The SR-71's flight ceiling of Mach 3.2 was, therefore, the absolute limit
that the titanium airframe could structurally tolerate.
The aircraft was a monument to material science, pushing the boundaries of what was possible.
While the SR-71 used early heat-resistant composites as radar-absorbing wedges, the manufacturing techniques for load-bearing composite structures did not yet exist.
Its successor, the developmental SR-72, will build upon this legacy.
It is expected to leverage new high-performance composites and 3D-printed titanium components.
Allowing it to reach speeds approaching Mach 6.
The SR-71's ultimate legacy is not just its operational record, but the engineering solutions it pioneered.
Proving that even the most extreme barriers of speed and temperature could be overcome through sheer ingenuity.